Hi Ben, how you doing this morning?
Hi, Benjamin. I'm good. How are you today?
I'm having fun. So I hear today we're going to talk about optimizing the trade-off between hydrocyclones and screens.
Okay.
Are you here to be my consultant and help me make this?
Well, we can talk about that. Absolutely. I think the first thing we've got to do, we got to pull it back to why we use something to classify either
Well, let's
hydrocyclones or
pull it
screens.
back even further. For all of
Oh,
the people who don't know anything about mineral processing, what is classification? Where do hydrocyclones and screens fit in the profit part, not the tailings management part, but the profit part of the business? So we're going to focus on how we make mines more profitable by using these versus how we manage waste better. So what do they do? What do these pieces of equipment do, Ben?
okay. So what we generally do, what they generally are used for in the circuit is size classification. And
What
where
does that mean?
hydrocyclones are probably the industry standard, they're put to close in a milling circuit. So the big tumbling mill will throw steel balls around it and break rocks, and then the particles come out of that. Some of those particles are going to be the right size for the downstream process to extract the valuable minerals. Some of them aren't going to be. So the role of the hydrocyclone is primarily to classify those particles. So to separate them based on size. That's what classifying is. Um, and send the stuff that's too coarse, so too large in size, back to the mill for further grinding, and send the stuff that is ready to be separated, so in that correct size range, to the downstream circuit. So in a big copper sulfide mine, it will be sending them to the flotation circuit.
And on the downstream circuit, if size is not big enough or size not small enough, what happens? So if you have this optimal
Yeah,
size you want to be in, what happens if you go ultra small stuff or big stuff? What happens to your recovery if you don't
yeah.
get size right?
Well, most processors have a sweet spot, a size range where they're really good at recovering minerals. So flotation, it's probably from about 5 or 10 microns up to about 200 microns for conventional flotation. In that zone, there still is a curve and a maximum. So there will be a size that is absolutely brilliant for recovery. But after that 10 micron, below 10 micron and above 200 micron, recovery falls off drastically. Basically, because the process isn't suited to particles that size. So ideally from this classifier, you're going to get a very narrow size range of particles that are all within this liberation zone. On top of that, just because it is in the right size range doesn't mean it's liberated. And that's effectively what we're trying to do with the comminution circuit, so the breakage circuits at the front of a mineral processing plant. We're trying to break the valuable mineral away from waste material. And the place where that's optimum is your target liberation size. So it's doing the minimum amount of work you can do to get sufficient liberation that you can actually recover those particles.
And you're looking to expose the mineral. Unless you have exposed mineral on what you break, it won't float. So if it's too
Yeah.
big, you can have embedded minerals that are never seen.
Yep.
And if it's too small, there isn't enough of a surface area for the bubble to attach. Is that basically what you're saying?
No. If it's too small, now you're trying to trigger me. If it's too small, there's a good chance that it's just not going to attach to any bubble. The probability goes right down, and it's going to end going to tails. It is a surface area thing, but it's got a lot more surface area when it's small.
Okay. So basically what you're saying is size does matter
Size
and
does matter.
and can't be a size queen, and you also can't be a size diva. So you got to be somewhere in the middle.
After 3 days hanging with my wife and daughter and hearing about Taylor Swift's new song and references to redwoods in terms of size, I'm happy to say that size, I can confirm that apparently size does matter.
It
Yes.
does, especially when you're dating a football star. Okay. So now we're going to move on. So you basically have got two choices. You got the choice to manage size by either using hydrocyclones or using screens. Is that basically the two choices, or is there another choice?
Look, I think there's a few choices out there. Let's come at that at a different angle, Benjamin. The typical way of doing this for the last, I'm going to say 50, 60 years, probably is 50, 60 years now, are hydrocyclones. They're cheap, people know how they work, and we use them. The problem is hydrocyclones
Are cheap.
No, it's not that they're cheap. That's a good thing. They're cheap. We all know how to use them. They're also very scalable. That was another thing. Mines that do hundreds of thousands of tons per day through a circuits use them. Small mines that may be doing 1,000 tons per day use them. So they're kind of versatile and they're fantastic. But there is a downside. Just because of the nature of the way they're classified, they don't purely classify on size only. They also, the specific gravity, so the weight of the minerals does have an impact. And because this does have an impact, you also see fine particles of heavier minerals reporting to the stream that's going back to the mills. And there's a big problem with this. The problem with this is those particles that are probably the right size and the right liberation to actually get recovered in the downstream process, they're going back to the mill, and chances are they get reground and get to a size that's fine, that doesn't like being recovered. So basically you're losing recovery, but also you're using a lot of energy regrinding these particles that are actually at the correct size.
And and let me make sure I understand this. And you're regrinding the heavier stuff, which tends to contain the sulfides. So you tend to be regrinding the stuff that's more valuable versus the waste. So the waste comes out cleanly, but the stuff you care about potentially gets too small.
Yes. Obviously, when there's a density effect, there's lighter materials and heavier, and sulfide minerals are usually heavier.
And
Sulfide minerals, gold, this is also a phenomenon with gold. You'll do that a lot, and it makes it really difficult to recover with gravity.
okay.
Hence the advent of a number of machines for both sulfides and golds used to scavenge that screen to try and address that problem. Things like Nelson's, flash float cells, and things like that. But they're not addressing the underlying classification inefficiency. They're just trying to scavenge out anything they can before it goes back and gets reground.
Okay. So let's work this through in a rational way.
Okay.
We have a system.
Yes.
We have choices. What is the prize? What is it worth to get this right? Like, we're living in a world where people are trying to get things right and they're trying to get them wrong. How much money is on the table for doing this right?
That's a really interesting question. And to answer that, you've got to work it through. The question is, if you haven't got the size distribution right, and you've got too many fines or too much coarse, you're probably not recovering that. So you're losing out on recovery in the downstream process.
Okay, so how much percent can you be off recovery?
Once again, it's going to be very operation specific, but I'd say in a lot of cases,
stop being an engineer and answer. Like, you are worse than a conscious critter going up. You're worse than one of the current administration creatures going up in front of Congress for review.
Ooh. No, I'm not. I'm giving you an answer. I'm just saying, I'm just using the metallurgist answer. It depends. So it's not one size fits all. But I think if you're starting to not get the correct size, you're probably losing a few percent recovery.
Okay. So fine. So let's play with a hypothetical mine. We have half a percent copper head grade. The raw rock is copper's $10,000 a ton these days. So there's 5 kilograms of copper in that ore. Does that sound about right?
Yes.
Okay. A kilo of copper is $10.
Okay.
So there's $50 of copper in that ore. So we've got a $50 raw rock. What you're saying is, if you get this wrong, it costs somewhere between 50 cents and $1.50, because every percent you get it wrong is 50 cents.
Okay.
Does that sound about right to you? Are we in the right order of magnitude, or are we wrong?
Probably there and thereabouts.
Okay,
yes.
Cool. So we got a 50 cent to $1.50 prize. And how big can these operations be? How many tons a day are we talking about?
Well, large copper mine, 200,000 tons per day. Easy.
Okay, so you're telling me this is a $36 million to $100 million a year problem you're solving in margin.
Yeah, it's worth
Sorry.
getting right.
Okay, cool. What does it cost in spares, wears, pump, everything? How much per diametric ton are we talking about? Order of magnitude around a hydrocyclone. What do you think what's the cost structure? I know the number, but I'm curious if you do.
I don't know the number off the top of my head. I know you know it.
It's probably about 9 cents to 12 cents a dry metric ton.
Okay, I was going to go slightly lower, but let's go with that.
That's buying all of your spares.
I was going to say about 5 cents, but you add pump and other things, you're probably right.
Energy and everything. Okay, so we're 10 cents. You get this right, this process can generate you 5 times your costs easily. And then you get this super right, you can make 15 times on your investment on optimizing the equipment.
Yeah.
It's staggering. And
it is staggering.
Yeah. And the costs, I mean, now let's flip the screens.
Wait a sec, but let's go back. It's magnified even more. Because typically plants are designed for a certain size, cyclones are set up a certain way. But what invariably happens because of our culture of let's push some more tons in, because everyone understands tons, more metal in equals more metal out. We jam more tons in, which inadvertently forces the cyclones to be less efficient, spewing out more material that isn't at the correct size, and that's adding. On top of that, as that gets more efficient, the amount of bypass material increases, so your circulating load's increasing, so your mill is seeing more and more material to grind, and you're using energy to grind stuff that you may not necessarily want to be grinding again. So there are other benefits as well from getting that right.
And we're talking about 8 kilowatts per trap through the mill? 8 kilowatts?
Yeah, depending on the ore, depending on the size, depending on how it all comes out, but it adds up pretty quickly. Plus the wear and tear, etc., etc., etc. So there's a lot of good reasons to actually go in and try to get this right.
Cool. So we're working all of these numbers through. We're working through all of the bits on these things. We're figuring these things out. And I'm not trying to be difficult. I'm trying to understand these things.
You're never difficult, Benjamin.
I specialize in being the queen of difficult. Let's be clear here. We're not going to cause any sort of trouble. So we're going to come in. We're going to look at an operation. And the first statement we're going to say is, hey, what's the price on the table? The price on the table you're saying is a minimum of 50 cents per dry metric ton and a maximum of $4 based on all the math you've given me.
Okay.
Between regrind, between energy savings, between debottlenecking value, between reduction in capital charges, and between primary recovery. You add up all those different value cases, and you're sort of between 50 cents and $4 per dry metric ton.
Okay.
I can buy from Krebs their best, most beautiful hydrocyclone pack for less than $5 million installed. The most expensive equipment package I can buy is $5 million.
Okay.
So these things should pay back in less than 3 months. Does that sound about right? Optimizing them?
Yeah, they're not an expensive bit of kit.
Okay.
Absolutely.
So cheap bit of kit, quick to do, quick to make decisions. And my bet is people just forget about them because they're cheap to buy, so they're not viewed as needing to be optimized. You're focusing on optimizing the mill because it's expensive, and you ignore the hydrocyclone because it's cheap. Yet it sounds like what you're saying to me is that it's cheaper to optimize the hydrocyclone to fix the mill.
Absolutely. We spend millions trying to figure out the mill, and I get it, it's a big risk. Whereas cyclones are incredibly cheap, and I think people sort of overlook them.
So how would you want to go into an operation and do this? Do you want to go in first and look at this as part of a holistic thing? Or do you want to first find low-hanging fruits like roping issues or this or that? What do you, how would you, if you were given, let's theoretically say that tomorrow BHP calls you up and says, Ben, get rid of that Benjamin dude because he drives us crazy. But if you just show up and you feed Benjamin information through a spaghetti wire and he stays away, because I mean, I might be loved or not loved, depending on who we're dealing with. How would you want to frame this? How are you going to create the goalposts of value? What is your minimum value? Just the recovery? Or is it just stopping mistakes on run roping? What's your very lowest value case you have on optimizing hydrocyclones?
Look, you introduce a new point, and giving Benjamin a little bit of information is dangerous. He loves now roping. Roping is a condition basically where your cyclone's not functioning properly. It can happen due to a few reasons, but basically you start getting all your material just going to the underflow, and it's not classifying at all. It is quite a common phenomena in a lot of operations, and even if you only lose one or two cyclones doing it, and it only happens once a shift, there's probably a fair bit of material that's going to the wrong place, which is something that's never good. Look, I wouldn't even go there first. I think that's a step, an early step, checking at how the cyclones operate and is there some gross instability there which may cause them to go into rope. I think understanding your cyclones, making sure they're up to spec. Once again, basic equipment stuff. Is the equipment running how it was designed to run? Do you actually know there's a few variables you can change in them relatively easily by changing the size of various components like your spigot and vortex finder? Checking the basic condition. Is it worn? Is it worn too much? Is it going to be changing the classification? How are they running? Is the pump worn? Is the pump supplying the pressure it needs to and the flow it needs to? Is there something else wrong with the system? So that's pretty basic stuff to check out and review, and you can work with your manufacturer to do that. But I'm a big fan of, if I'm going in to look at, is there an impact on recovery? I'd be going straight to the tailing sample, getting a decent tailing sample or a composite over a period of time you're looking at, and doing some mineralogy, having a look at where the losses are. Are they in coarse sizes? Are they in fine sizes?
Okay.
Is there something there pointing at either the separation circuit, or is it definitely a liberation issue, too coarse or too fine?
Okay, so you're going to start with tailings. Assuming regular equipment maintenance is fine, you're going to start with tailings.
Yeah, we're going to see if there is a problem.
Okay.
There's other ways of doing it. Don't get me wrong. There's ways of going back to first principle, checking the size. Look, and at the same time as looking at the equipment, how is the control around those cyclones? Have those control loops been tuned? How are the operators running them? Is it running them to keep a mill happy or something, or is it running them to get the best result out of them? Because things like that happen. We've seen that before. We go into a place and a certain bit of pump is run a certain way so it doesn't overflow and make a mess, rather than saying, hey, we should get a different pump.
So let's work this backwards. What you're telling me is you're going to take a sample a day from your tailing stream, let's say for a month before you show up, send them off to a lab, take a look at them, see if you got a problem. You're going to look at the basic equipment, and you're telling me the prize is somewhere between a minimum of $30 million a year in earnings, upwards to $300 million a year for a decent sized mine, for getting it right.
Yeah, depending on the size of your mine. Doing that tailings exercise straight up is going to give you that answer.
Cool. And what is the cost of doing all of this? Assuming you hire the EPCMs, assuming I hire you as quarterback, and we do all of it.
I don't even think you need to go to that extreme. This is something plant metallurgists on site can instigate and do themselves. Now, it's been many years since I've done mineralogy on tailings, and back then it was one of the more expensive analyses, but you're only talking, if you're doing a lot of it ongoing, you're only talking tens of thousands of dollars. Okay. And it's probably significantly cheaper now because we've come a long way.
So your ante to do this, not to pick on someone's name, but your ante to do this is going to be in the order of magnitude of $50,000 to $200,000 with a potential river that's worth $50 million.
Easily.
Okay. Why don't people do this? You can't be that unique that only you have figured this stuff out. Why is this not being done if the return on risk is that high? What's everyone missing?
I think it's cultural. I think we often turn up in plants, and the plant's been running that way. And don't underestimate the resistance to change for doing something different. I've seen plants where they've found they've got recovery problems and they've fixed them, and they still don't want to admit they've had a problem in the first place. So I think people fall into the trap that the plant's producing, we're making enough metal, no one's screaming. I don't want to rock the boat and try for a little bit more.
And you still don't want to admit that you need a proper head raiser. So, I mean, let's be clear. Resistance to change happens with many metallurgists. You're convinced that you've got the exact right clippers, and once a week is the right optimal time to shave your head.
Oh, here we go. Yes.
You know what I'm going to do? I'm going to send your wife the proper kit.
No, don't send my wife. We'll never hear the end of that.
Oh, we will never. That's why it'd be so entertaining. But you see, this is the problem with change. You have to figure out who the actual investor is to get the change.
Yeah.
Sometimes it isn't the metallurgist. Sometimes it's the person who manages the metallurgist, i.e. Ben's wife. Are
you having fun, Benjamin?
I am having lovely amounts of fun today. I am enjoying life. Life could be so much worse. Let's come back. Let's start wrapping this up. So basically what you're saying is we got a problem.
Yes.
You could do every mine on a tier 1 portfolio for less than $1 million. You could optimize and figure that out. You're pretty much guaranteeing a 500, 800% ROI on that. No questions asked, and probably measured in the tens of thousands % return on investment of going through and looking at every mine, optimizing them, and checking this one particular variable.
Yes. Especially if you had a portfolio of mines, even if you miss 9 out of 10, the 10th is going to pay for the other 9.
So the key is to systematize it. The key is to do the same thing. The key is to know what you're doing, and the key is to understand the value case. I would argue that what people are lacking is the ability to say, hey, what is this worth? Not, is there a problem?
Yeah. And I don't think that has been the traditional way of doing things. I think our culture in the industry is very much firefighting. You see a dip in recovery or a dip in throughput, phone calls will start happening down the chain of management and end up with the poor old metallurgist. And they will be jumping around, chasing this problem to fix it. And yet we don't take enough time to look at some of these fundamental things and put in a proactive plan to manage, make sure they stay in range and fix them. And it's not everywhere. We've seen, years ago, I worked in many plants and they would measure. Interestingly enough, they'd measure based on one random size fraction and try to track what was coming out of the hydrocyclones. Wasn't perfect, but over the last 30 years, I've seen that fall off in a lot of places. Some people have taken it up with online analysis, which is fantastic. Some people try online analysis but don't invest to maintain it. So it's always measuring size and it's working correctly. It's one of those things. I think through some of the complexity we've introduced, we've lost sight of some of these basic things.
And let me get this right. You're not suggesting that you want to do the engineering or design the new hydrocyclone or do any of that stuff. What you're suggesting is you want to play quarterback and help design the way to maximize the value versus run an engineering team to optimize each site.
Absolutely. There's good engineering teams out there. I think a lot of this work can be done by people on site initially to identify there's a problem, and then they can go talk to an EPCM or another service provider to actually start working through solutions, because chances are you may have to change parts of the plant when you get to this, when you identify this problem. And there's a group of people who are really skilled at doing that and are set up to do that. So definitely engage them. It's all about using the right tool for the right job. But I think the site focus should be at first making sure, checking if there's a problem there, and if there is, starting the ball rolling to get the solution done.
And your right tool is the fact that you can see it from all sides, and you're lazy enough that you don't want to do the engineering and you don't want to do all the fine tuning stuff. So you're not going to eat other people's lunches.
Absolutely.
What you're looking to do is you're looking to come in and play quarterback.
Oh, look, absolutely. If someone goes and gathers this basic data, really happy to help quantify that for them and build a justification and a business case so they can go forward and get the right people to help them fix the problem.
Cool. Okay, so let's wrap this up. Next time, we're going to talk about control systems, primarily on thickener and water. But what you're telling me is that you think that there's an opportunity here to make any mining company a few $1 billion of MPV for less than a few months of your time.
Absolutely.
Lovely. And by the way, I pimp Ben out for only the rack rate of X $1,000 a day, so he's pretty cheap. Sorry, I'm teasing.
If I shave my head more appropriately, would that be more?
Oh, it would go way up. Like a decent, proper banker head shave, and I get you the proper collarless shirt. And you don't tell bond traders that they trade paper and have them talk about paper mills. I think it could probably triple what you get paid.
I'm sure paper mills are more fun than bond trading.
You know, paper derivatives and bond trading is way more fun than paper mills. All depends on who you are. On that note, this has been fun. We'll see you next time about thickener control systems and other interesting plant modifications as we work out how to build and the value case of optimizing natural capital.
Excellent.
See you next week.
Look forward to it, Benjamin. Bye.